So this is the last referee paper for tonight, and therefore Lancrenon, the floor is yours. On passwords and authenticated key exchange,
Okay. Okay. Well, thanks for the opportunity to speak. So I'm Jean Lancrenon. I'm a postdoc at the University of Luxembourg, and I'm going to talk to you about an interesting, what I would expect to be an interesting crypto primitive for an audience like this, which is password authenticated key exchange, and more specifically, the modeling of this primitive in the crypto world or in the provable security world. So it's basically a two-part talk where I start by explaining what password authenticated key exchange is, and maybe giving you, I've been asked to give maybe a small, definitely not exhaustive list of some of the protocols that exist. And then I'll talk to you about security model definitions, and specifically some little differences between models that bother me. And I'll tell you why they bother me and how I've tried to maybe not correct them, because that's a bit too that would be a bit too exaggerated, but how I'm trying to at least understand them and how I'm trying to interpret them or make adjustments to help out. So it's the Alice and Bob setting of the crypto world, of course, where you have Alice and Bob who are trying to run some cryptographic service over a network, and to do so they need to share some session key for that, only they don't know what the quality of that network is, in the sense that there might be some attacker in the middle. So the best way to do that is to run a key exchange algorithm that has authentication attached to it or incorporated into it. And password authenticated key exchange uses as a trusted setup passwords. So Alice and Bob each hold a password, and the basic correctness requirement or function, the basic correctness requirement of this primitive is that if the two entities are running this protocol, then they're going to end up with the same session key if and only if they have the same password. Now this can be a little bit modified. One user can have a hash of a password and the other one can hold the actual password. But those are small differences that don't change the functionality very much. Something I didn't write on the slide is the session key they obtain is high entropy, whereas the password, of course, is low entropy. So it's a way to kind of bootstrap high entropy security from a low entropy secret, which is quite unique in the crypto world. Of course, as you all know, this is fundamentally different from usual key exchange protocols, which rely on public key infrastructure or shared secret keys that are AES keys or things like that. Passwords being low entropy, they can be brute forced. So you can't have a secret key that is the password and to have a public key that corresponds to that password. It's just not going to work. Of course, the brute forcing of passwords is possible only assuming that they can be verified. So it's the verification of guesses that's crucial to pay attention to in these protocols. And there are two types of, we usually classify the attacks on PAKEs in between offline dictionary attacks first, where what happens is you have all of this data flying around on the network between honest users. So these arrows represent either protocol runs of the protocol itself, or they can represent session keys that are used in higher level applications. All of this data depends in one way or another on the passwords that were input to the protocol. Of course, in an offline attack, the adversary, who is the network, gets to see all of that and tries to correlate the information that it sees with password guesses of its own. And this is only useful for him if he can do this with efficiently computable functions and some dictionary. So offline attacks are essentially eavesdroppers that are trying to correlate password data with what's flying around on the network. An example of a bad PAKE protocol that would do this is something like this, where you want to authenticate a Diffie-Hellman key exchange by just binding the password to the Diffie-Hellman key exchange itself using a hash. This is obviously a vector for an offline dictionary attack on the password. So in PAKE protocols, when we're trying to prove things, we want to eliminate offline attacks completely. And we can do this. It's possible to do this. I say it's possible to prove it at least, because then it depends on what you consider proven, depending on what kind of idealization you make in a provable security framework. So I'll say a few words about that later. In online dictionary attacks, you have something a little bit different. You have an honest user which is expecting to talk to somebody else that's honest and engages in a protocol run, but is actually talking to a malicious adversary who is trying to infer information on the password like that. So that's an online attack. The online attack means there's interaction, basically. And testing is done directly through this interaction. And the prototype of such an attack is a simple login attempt. What's particular about online dictionary attacks is that in the PAKE service, when we're trying to model it, it's something that we can't avoid. It's something that's inherent to the service and that crypto can't do anything about, at least not at this level. So we have to factor that somehow into the security model. What we can't do is eliminate them, but what we can try to do is make sure that login attempts are the only possible ways of attacking the system. So here's a slide I added last night, which kind of recaps some protocols that exist out there. Basically, PAKE research started as early as 1992 with encrypted key exchange, which you may have heard of. That was invented by Belovin and Merritt, and it basically entails of a symmetric key encryption of a Diffie-Hellman key exchange, with the symmetric key itself being the encryption key. So EEC has been analyzed in what's called the ideal cipher model of crypto, but it's very difficult to implement to avoid offline dictionary attacks. It's tricky to implement. Another example is Speak, which you may have also heard of. These two are kind of the most known because they're also the ones that have caused the most trouble from a patent point of view, I've heard. I've heard that people have tried to deploy PAKEs, but it's hard to do so because they keep getting patent roadblocks, and it seems to be essentially due to these two, because a lot of protocols are kind of variations on these two, especially on EEC. One example of this is the PAC and PPK protocols that came out in 2000. PAC provides explicit mutual authentication. PPK provides implicit authentication, so there are different security properties you can look at. There's a protocol from 2001, which was kind of an important one, at least from the theory community, from Katz, Ostrovsky, and Yoon, where the idea here is they were able to prove secure their protocol, and what's specific about this protocol is that it doesn't require any random oracles or ideal ciphers to get a proof to go through. So it's a standard model protocol, but it comes with a different caveat that that I don't want to get into right now. It's also less practical. A lot of protocols spun off of this last one in the sense that they're secure without idealized assumptions. They're secure using standard number theoretic assumptions, but they also cost more to implement. I mean, they have a lot more group multiplications and exponentiations than the ones that rely on random oracles. So they tend to be much less practical. They're theoretically efficient, but they're much less practical. And I don't think they've been implemented so much. And there are other, So there's the JPEG protocol by Howe and Ryan from 2008, which is secure in the random oracle model, but is the structure is sufficiently different from the previous protocols that this one isn't bothered by patents, I think, it seems. So Mozilla, for instance, used this in some of their features. I don't think they use it anymore. I can't recall why. There's also a protocol called Dragonfly by Dan Harkins from 2008, which kind of looks like the Speak protocol from Jablon, but is sufficiently different that maybe it's not bothered by patents. And there's a whole bunch of other protocols that the theory people have come up with over time. So it's not there isn't a lack of protocols, but yeah, maybe we're not so good at communicating that. So now I'll talk a little bit about security models. and the problems that I kind of have with them. So first, there are many models in the literature, starting with the Bellari, Rogueway, and Poincheval model from, which I'll just call BPR. That was a so-called indistinguishability-based model. Then there's a model by Boyko, McKenzie, and Patel, which is one of the simulation-based models. Canetti and the list of 4 other authors that I don't recall came up with a model for PAKE that's universally composable. Yet another one. Goldreich and Lindell came up with a model just so that they could have a framework to show that PAKE is possible under standard complexity theoretic assumptions. So that's already a lot of models, so it's hard to see which one is the good one, if there is a good one, which is already kind of something that bothers me. But it gets a little bit worse than that. So within the pool of models that exist, the most successful ones have been the Bellari, Poincheval, Rogueway one, which I'll describe soon. And it has an important follow-up by Abdallah et al. From 2005. So we're going to focus on these. And already in this kind of subclass of models, there are little technical differences between models that make it kind of difficult to assess security somehow. So I find it difficult as someone who looks at this a lot. I can't imagine what it's like for someone who's a practitioner and who wants to get some assurance that a protocol is correct or is secure. So I'll get into a quick description of the BPR model and how it works. What we start with is a fixed collection of users, which is usually separated between a bunch of clients and servers, but that's not very strict. And our adversary is a polynomial time adversary, which just represents the network. And it's the one that communicates with these users. Now, before your security game begins, each client is assigned a password that, for simplicity, is selected uniformly at random from a password set. And each server is assigned a vector of passwords from all of the clients. So these things can change also from paper to paper. More specifically, the attacker isn't going to talk to users. It's going to talk to user instances. And you can think of a user instance as one run of the protocol being attempted by that user. So we just index these instances with integers. How an instance functions is it gets instructions from the adversary and reacts to those. It reacts according to protocol specification. Eventually, it might compute it might compute a session key, or it might reject messages. But if it computes a session key, then it thinks it shares this key with what it believes to be its partner. And the way the adversary communicates in the model with these instances is via queries, various queries. So for instance, you have the send query, which delivers messages of the adversary's choice to these instances and sees what happens. If a response is generated, the adversary gets it. The execute query just runs the protocol honestly between 2 instances and gives the adversary access to a whole pool of honest protocol runs to eavesdrop on. And the reveal query, basically, what we do is we don't know what the quality of the algorithms our session keys are going to be run in is. So we pessimistically assume that the adversary can just obtain any session key it wants by observing the network. The idea being that if a session key is disclosed, that shouldn't damage the security of other protocol runs. And we have this special test query, which is used only to measure the adversary's success in a model like this. So how the test query works is once it's invoked by the adversary, you flip a bit, and what the adversary gets in return is either a random key if this bit was nil, or the actual session key that was computed if the bit is set to 1. And the adversary's goal in the whole game, the way we measure the adversary's security, is to check first to check if it can output a correct guess on this bit or not. So the adversary wins the game if the bits are equal, and it loses otherwise. So what we want to, we're trying to measure what we call the semantic security of the session key. N's advantage in winning is typically this. For ordinary authenticated key exchange, the advantage is defined as being twice the probability that it wins, minus 1. And when you're looking at high entropy based protocols, we require this to be negligible. We can do that because the long-term key material is high entropy. But for PAICs, it's a bit different. We can't do that because we have to factor in the fact that there are online dictionary attacks that are possible, and these will succeed depending on the size of the password space. So rendering those negligible isn't an option anymore. So we have to change our requirement a little bit. The requirement on the bound that we want now is this. We want to make sure that the advantage is smaller than a constant times the number of send queries divided by the size of the password space plus some negligible chance. So here, C is just some constant. It represents, intuitively, it should represent the number of passwords that can be ruled out in one login attempt. But, so ideally, we'd want this to be 1. The number of send queries is basically measures the number of interactions with instances, and PW is the password space. This is taking longer than I thought. So the definition is only meaningful after we've added a restriction, however, because we don't want to be testing a key that's already been revealed to the adversary. So what we need to add as a restriction is that a user instance can't be tested if its partner or if itself has already been revealed. And that's where a lot of problems begin, at least for me. So maybe I'll skip a few things here to get to the point. The point is, we don't really know what a partner is anyway. This is the thing that changes from paper to paper. Intuitively, instances are going to be partnered if they've had a correct exchange, but we don't know how to we can't seem to formalize this very well or consistently across papers. So it makes assessing security, at least from my point of view, it seems to make assessing security difficult. I don't see how you can trust the security in one model of a protocol if it's secure in one model, but that doesn't carry over to another model. So I guess one takeaway from this talk is that there are a lot of technical variables that are used to keep track of what key moments in an instance's life during the execution, which would be when it's willing to use a session key, when it stops, when 2 instances are partnered, and these are things that change all the time. So in the paper, what I tried to do is come up with a consistent way to put all these together, which kind of sounds like I've added. So I'm going to skip all this because these are details that are going to take too far. But it kind of sounds like I've just proposed another model, but I don't see it that way. I just see it as an adjustment to the ones that kind of exist. And I couldn't see myself complaining about certain things without trying to suggest something, not to replace, but at least to try to explain the others. One thing that I found particularly annoying is in the partnering definition, there are 2 different kinds of philosophies. Some of them are going to have a partnering definition of this form. You have a list of technical conditions and on 2 instances, and these instances are unique in satisfying these conditions. Or sometimes this condition is dropped. And I found that this causes a bug, at least it causes a bug in certain models definitionally. And I wanted to try to fix this bug so that at least it made more sense to me, and maybe it'll make more sense to other people as well. This uniqueness thing has also bugged me in another way. So in the paper, I show that if I keep it in the partnering definition, then it causes trouble definitionally. It causes a bug in one of the models, which bothers me. But ignoring it completely is ill-advised as well. So I won't go over the bug because it's technical and I'm running out of time. But the other thing that, so now I'll talk about what happens if you try to eliminate uniqueness completely from the definition. So uniqueness of the partner is something you would require in any authenticated key exchange protocol. It's a natural requirement. I want, if 2 instances are partnered, they should be uniquely partnered. There shouldn't be a 3rd one hanging around. But this requirement, oddly enough, has vanished from authenticated key exchange papers, not just password ones. And that's a little strange because the very first paper on authenticated key exchange had this as a property that was proven. So I found that weird. one reason, I guess, for this is that some people, or it seems to be assumed that maybe session key security implies uniqueness of partners. But by reasoning of this form, multiple partners would imply violating the partnering. So I have to quote partnering because if you have uniqueness or not, then partnering is formally invalidated. This would imply an illegal way to distinguish session keys from random and therefore would be captured by the definition. But first, technically I couldn't get this to work. Maybe somebody has, but I couldn't, not in any straightforward way. And secondly, even if it did work for password-based key exchange, this wouldn't even help us because the security bound that's optimal in PAKES isn't even a negligible bound. So we can't even guarantee unique partners with with overwhelming probability, even if we just relied on session key security. Now, it's in the literature, the PAKES that you find who have security proofs don't suffer from this because of the way the partners or the partnering function is defined. It's a function of the randomness of both partners. So there's always going to be the randomness of the partner included in the way the partnering function is computed. In the paper, I found a protocol which is kind of convoluted, but that shows that you can create a PAKE, a kind of PAKE, that allows multiple partners with a non-negligible probability, but at the same time has a security proof in a model where you don't pay attention to this uniqueness stuff. So I really think that uniqueness of partners, among other things, ought to be an explicitly proven property, even if it's easy to do. It's very easy to do. It's almost the first thing you prove when you're going through a PAKE security proof. I find it would make a more complete and a clearer model, and that it would make more sense mathematically, because if you have, I say make more sense mathematically because the definitions, if they have bugs in them, then it's kind of, I find it pointless to try to do something mathematically with definitions that have bugs in them. If you're not precise, it's just not, it's not real mathematics somehow. So if we want to do this in a provably secure way, we need to make it as mathematically credible as possible. So I think I'm done. So I'll just stop there, and I'm happy to take questions. Yeah.